Okay, so I think this week's kind of interesting, straightforward, good stuff. We're going to talk about categorical difference tests. I found a few different examples than the book, so we'll go through the lecture examples first and then the book. I think that way you have two different perspectives on it. All right. I did want to do an example. I didn't realize my license was expired on here, so. But I might be able to fix that up while we're going. Display settings. Okay, so there we go. I tried to remove the background graphics, but I guess I still have the wood floor there. So we're going to start off talking about categorical difference tests by talking about something that we're probably all familiar with. Here, rock, paper, scissors, right? So we've got the game everybody knows. You go 1, 2, 3, and then your rock, your paper, your scissors. And paper beats the rock, and the rock beats the scissors, right? If we wanted to come up with a kind of like a statistical test to see if somebody was more often prone in their mind to choose rock, paper, or scissors, what we're going to talk about today would be a good one. So this is a good basic example. It's not really a real-life example. We'll do those in a second. But this is a basic example of one of the subjects that we'll be talking about today. So what we could do is we could play with somebody, this game, rock, paper, scissors, and record the number of times that they did rock, paper, and scissors. So today it's all about categories, which has been different than we've been dealing with recently, where we've been using numbers exclusively. So the math is a little more straightforward here. We're dealing with counts, and we're gonna compare counts in categories between what we actually observed. In this case, this is the observation to what was expected. All right. So in this case, we might want to test whether or not for a particular player, all the categories were equally likely. In other words, were they more prone to pick one of the categories, or are they pretty good at just being totally random? All right, so in this case, when we want to test whether or not each of those categories are equally likely, we would state the hypothesis, and the null hypothesis would be that a particular player, based on observations, was equally likely to pick rock, paper, or scissors. The alternative hypothesis would be that they were not equally likely, that they had some bias that chose one over the other, one category over the other. So today's statistic is going to be the chi-square statistic, okay, our test statistic, and that's what we're going to be calculating to test our hypothesis. So talk about how to calculate that in a bit. It's going to be based on our sample data. This next thing is, it says create a distribution of this statistic as it would be observed if the null hypothesis were true. And in our example, the null hypothesis is that each category is just as likely to be chosen. And so the expected distribution of that variable is that there's an equal number in each category. And then finally, just like any other test, we measure how extreme your test statistic is and compare it from the distribution generated. So here is our hypothesis in general. So P is going to denote the proportion in the ith category. So we have a number of categories. It's a categorical test. Number of categories, P is the proportion that we should expect. So the null hypothesis, like I said, they're all the same, or another way to say that is they're all equal, which is what I said on the last slide. And then at least one proportion differs from the others. Okay, another way to say that is that we have 1/3 of the values in each category in this case. Okay, this is specific to our current rock paper scissors scenario. This is more general. And in both cases, well, I'll talk about that in a second. So the observed counts are the actual counts that are observed in the study, whatever the study was. This could represent actual respondents, like you go out and survey people, and you ask them if they're, well, the one from the book, you ask them if they're satisfied or dissatisfied with Congress. Or you could ask, are you satisfied, somewhat satisfied, or not satisfied? You guys get asked that same question at the end of the semester, right? Like, are you satisfied with Dr. Raber, unsatisfied, or whatever? So you could use those types of studies. You could also, like being geographers, we could change this to if we had geographic data, like GIS data, and it was categorized by income levels, high, medium, and low. Okay, we could see if income levels were uniformly distributed or distributed in some other way. But we have to boil our data down into counts. So here we have already shown that thing, rock, papers, and scissors. So it's the observed. And the expected are the counts if the null hypothesis were true, which in our case is simply just the expected proportion 1/3 divided by n, the total number of observations. So sorry, I should have actually put it up on here. Maybe I did in a second, I forgot. But let's go ahead and calculate. So these are the observed values. And when you're doing these kind of test statistics, this chi-square test, or does it fit? In this case, it's the uniform distribution. Okay. What you have to do is you have to take these numbers and distribute them according to what you would expect. So if this is a uniform distribution, you would expect there to be an equal number in each category, but how much would that be? What you do is add up all of the observations. So 66 plus 39 plus 14. And then you add up 66 plus 39 plus 14, and you multiply that by 1/3. You put that number here, and here, and here. So, yeah, so I guess I didn't calculate it. Oh yeah, I did. I just put it out of order. I meant to put that slide up before this slide. Okay, so the expected values are in this slide. Sorry about that. So they're about 40. Okay? It's okay to use, for this particular test, it's okay to use decimal places in the expected counts. So 39.7 in each one. And what that represents is the total of this multiplied by the proportion in each category. And that's the general form you're going to follow for whatever test. Okay. So the chi-square statistic is computed from the data, and that's what we're going to use to assess a null hypothesis. Chi-square statistic is used for testing whether or not categorical data matches a particular distribution. In this case, a uniform distribution. So we take our chi-square statistic and test it for categorical variables. It's a really simple formula. We just take the observed values, we subtract the expected values, we square that, and divide it by the expected values for that category. And then we do that, we sum them all up for each category. I didn't put the little, it should have said like K and I and then K. So this is the number of categories. So we're going to do this 3 times. Each category is going to have what they call a contribution to the chi-square statistic. So we're going to add up the 3 contributions from each category. And then the categories is actually going to be the categories -1 is going to be the degrees of freedom. So here are the observed and the expected values. We simply take this number and we subtract this number, because that's observed expected, observed expected. So we subtract each of these 3 numbers from each other, and then we square those numbers, and then after we square them, we divide them by the expected, and then we add them all up. And then we have our chi-square. It's called chi-square, not chi-square, just in case you're wondering. All right, so this is pretty easy stuff. But Excel makes it even easier. Getting a phone call. Doesn't normally work, I guess. All right. So there's the numbers. So as I said, we can do this in steps. We just take this minus this. That's kind of the first step. And then we take this times this. That's the second step because it's squaring it. And then after we square it, so what does that actually imply? Well, I'll just tell you. So because we're squaring it there, the chi-square statistic is always a positive. It's always positive because you can't get a negative number when you square square number, because it's either a negative times a negative or a positive times a positive. Okay, so then when you divide it, we divide that number by the expected value, and these are the contributions of each to the chi-square statistic. So we add those all together, we sum them, and that is the chi-square statistic, 34.072229. That's the number. And all I did was implement this formula. Pretty simple formula. So what's next? We have our test statistic. What else do we need to perform the hypothesis test? Well, we're looking at a new distribution, one that we haven't looked at before. Okay, we're not looking at the t distribution or the z distribution. So we need to look at where that number comes from. Sorry, I think I actually, oh no I didn't. This is the distribution of the this is the chi-square distribution. All right? And it actually comes from the z distribution. So it's looking at a normal distribution, but it's squaring that normal distribution. Okay, so that's why it starts with this really high value when the degrees of freedom are 1 and tails off. And when it's 2, we get we're looking at 2 different z distributions. We get a curve, and then that curve tails off slowly as we get more and more degrees of freedom. As we have more and more categories. So we're always looking at the upper tail. We're not looking at 2 tails anymore because we've squared it. Okay, they're always positive. At the higher this chi-square statistic is, the further the observed counts are from the expected counts, and the stronger evidence against the null. So the degrees of freedom is the number of categories minus 1. And that's true as long as there are at least 5 expected counts. So you only should use this test if there are at least 5 in each count. All right? And then, you know, that shouldn't be a problem most times. But because either it's obvious that it's not uniform distribution if you get some that are below 5, or you could just go out and collect more data until you get at least 5 in each category. All right, so the number of degrees of freedom is the number of categories minus 1. So in this case, it equals 2. So we could look it up in the tables in the back of the book. However, the tables in the back of the book are fairly incomplete, but the F distribution. But we can still see that we either do or don't make the cutoff. Okay, so we look at our degrees of freedom of 2, and we try to find the chi-square value of 34, and we don't see it, right? The chi-square value of 34 is, the highest value is 26. But if you look at that note, the missing entries in the top right-hand corner give p-value greater than 0.2. All other missing values give p less than 0.005. Sorry, it's on page 3. It's actually called the table F, which is confusing because it's not the F table. That was table E. But it's on page 312. 312. Page 312. And so the chi-square values only range from 3.2 to 26. So we don't even go up to 34. And so we don't know exactly where it is. We just know that it's very either it's very small or very large. So we know whether or not to reject or accept the null hypothesis. Alternatively, Excel actually will calculate the exact p-value for you. Okay? So if, we've got the tables, and we can look up that number in the tables. But alternatively, Excel will allow you to run the chi-square test. It's really simple. It's kind of like we don't have to use data analysis. We just hit equal. I mean, we can, but there is to get just the number. We can say equals, and then type in chi. It's actually the chi-square test. Okay. And you have to give it the actual range and the expected range. So you just go chi-square dot test, and you check here's the actual range. We've used the word observed, so that's what it means though. And so you choose those values in the observed, and then you press comma, and then you choose the expected range, this. And you press enter. And here it gives you the actual p-value, what it is. Okay, it's very, very tiny. It's a very, very tiny p-value. So if it's a very tiny p-value, do we accept or reject the null hypothesis? In all the tests, it's always the same.
Accept.
Reject. Yep. Good job. What's that? Because it's under 0.05. If we probably should have set a an alpha value that we were gonna, but normally it is 0.05, right? But it's way smaller than that. It's It's really, really small. And so what does that say? Remember what was our null hypothesis? You can go back and look at the PowerPoint if you want. What was the null hypothesis? That they were all equal. So we rejected that. Does that make sense? Yeah. This one was a pretty big difference, right? I forgot whether this updates dynamically, but let's just say this was 40, 39. Yeah, it does. Okay, 40, 39, and 38. See how that now we have the same numbers and the same total. But look at the chi-square statistic. That number is 0.95. That number is really, really big. The biggest it can get is 1. And it's now on the other side of that cutoff, the 0.05 cutoff. So what would that mean? Should we accept or reject this time? Accept, right? So even though these numbers aren't exactly evenly distributed, it's possible that the person truly is random, but this time it worked out that way, okay? Because of randomness. Because randomness doesn't always produce exactly the same values. Sometimes they're off by a little bit. So we could experiment, maybe take 8 off of this, 30, and put 8 onto that. Now it's raining. Now we're still at the point where we reject the null hypothesis, interestingly. We accept the null hypothesis that they're equal. We're not down to 0.05 levels yet. So these could have been produced by chance, even with a normal distribution. Okay, but we're getting close.
So we would accept that one?
Yeah, we would accept that one.
It's larger than 0.05.
Right. Yep. We would accept that one. Wow. All right. So that's a simple example. So let's look and see. Let's try to do some other, a little bit more practical examples of the chi-square distribution. Actually, I'm just going to leave that right there for a second. Stop. Okay. So this is a pretty easy one to do in Excel, but there's lots of programs that do it. All right, so this goodness of fit, sometimes this is referred to as a goodness of fit test. So it tests whether a distribution of the category variable is the same as the null hypothesized distribution. So we did it with a uniform distribution, but it actually doesn't have to be a uniform distribution. You just have to have observed and expected. So the null hypothesized proportions for each category don't have to be the same. They can be different. So if you say, I should see a proportion like this, but I see a proportion like this, is it possible that that's just from random chance? Or are those actually not really the same to, is this observed frequency count not drawn from that expected true proportion difference? It's getting some rain. All right, so it doesn't have to be uniform. It can be, but it doesn't have to be. It can be any different type of distribution. So this is the kind of the general form here. So the null hypothesis for each category is that they match the proportions. The alternative is at least one of the proportions is different than specified in the null. All right, then you calculate the expected counts. calculate the chi-square statistic. In this case, I mean, this is the general form. It's always this one. It's in the book. You've got it in the book. It looks a little different because I didn't, like I said, I didn't put the notation at the top and bottom of here. So then you compute the p-values. Excel allows you to get the exact p-value, but the table in the book still allows you to get to the cutoff value, and so you know it's less than or greater than the cutoff value. Then you interpret the p-value and decide whether or not to accept or reject. All right, so here's a more practical example. So Mendel, Gregor Mendel, he, I don't know if you remember back in high school biology, we talked about this in high school biology. He had these experiments on peas. Basically, he hypothesized that that there were different characteristics of peas that were either dominant or recessive. And these characteristics that he first looked at were whether the pea was yellow or green, and whether or not it was wrinkled or not wrinkled. I forgot the and so his theory was that the recessive genes would interact in a way that they would basically, you would see less of them because both plants had to have the recessive gene in order to pass that on to the new plant. Whereas if they had the dominant gene, it would pass only on that category. So what he hypothesized was that he mated certain plants that had the recessive gene and plants that had the dominant gene. In 2 generations, you should see a distribution like this if it really matched his thinking. Okay, you should see approximately 9/16 of the plants having round yellow peas. Okay? 3/16 should have round green peas. 3/16 should be wrinkled yellow, and 1/16 should be wrinkled and green. So that was based on his genetic principles. Okay, because these are basically the small s's are the recessive gene. The large Y is the dominant gene. The large Y would be the yellow seed. This is the wrinkled yellow seed. So we counted up how much you should get for each category, and that's. So he was trying to decide, hey, are these theoretical proportions gonna actually happen? And so, of course, when you go about doing your experiment, you get a different number, and they're in counts, they're not in proportions. You get a different number, and they don't boil down to exactly 9/16 of the data, okay? Because there's some randomness involved in this. Right? You just know that you just theorize that the probabilities should produce this, but the numbers don't exactly match with your theoretical proportion. But what if I wanted to test, hey, could they have been drawn, assuming these were the theoretical proportions, could these observed counts been created from those theoretical proportions? So we're going to test that null hypothesis. So how would we do that? So this is not doing it with uniform distribution. Okay. So let's walk through the whole thing. I'm going to copy all of this into Excel. Oops. Because we need to get the expected counts in order for this to work. So I'm just going to do a new sheet. I'm going to paste I mean, if you want to paste all the colors, that's fine too, but okay, these numbers aren't right, so I'll just manually, actually, I think I can just go like this and say format cells, number. That's still not right. Okay, I'm just going to say equals 9 over 16 equals 3 over 16. Those were the numbers, right? Equals 3 over 16 and equals 1 over 16. So those are the proportions. It's probably best to convert those proportions, those fractions into proportions anyway. So these are your expected proportions. These are your observed counts. So what we need to do, just like with the rock, paper, scissors, we need to change our expected counts into, we need to change our expected proportions into expected counts. In other words, another way to say that is, if we planted the exact same number of plants, what should we have expected to see in terms of counts? And so the general formula for this is to calculate the total number of values and multiply that by the null in each case, the null proportion in each case, the expected proportion. So I'm gonna leave a space here. I'm gonna sum all of these values up. That'll give me a total. That's the total number of values. So what I want to do is I want to place 56% of those values here, 19% here, 19% here, and 6% there. That's all I want to do. So one way to do that is to say equals, I think it's $, this. How do you like lock it on a certain cell? Times this. Let's see if that works. Scroll down. Nope, that didn't work. Okay, I do know it'll work like this. I'm going to change this. So if you rename this, over here it's called C8. If you rename it total, or n, okay, then you can just write in n times b3. Now if you fill down, it will keep those values. So these are our expected counts. And remember, they're called counts, but it's okay to leave them as decimals. It's okay to leave them as decimals because they're going to be used they're going to be used in a mathematical formula anyway. All right.
Again, how you lock them?
How I locked the n. So I just I had to rename right here. I renamed this n. Once you do that, if you use n in the formula, it won't change it. See how it's n times b3. There is a way to lock it in the code. I thought it was a $, but anyway, there's a way to lock it without naming it, but I don't remember how to do it. This is the way I usually do it, is just rename it. Okay, so now what I want to do is to add up and figure out the contributions. Now I could, since this is Excel, in fact, I'll just do that real quick. Equals chi-square test, and then put in the actual range, comma, the observed range. So if I hit enter here, that's my chi-square. That's the actual p-value. That's not the chi-square value. That's the actual. That's the p-value. All right. But let's also do this again, where we say it's the observed minus the expected. Add all those up, and then square them. This times this. Add those up. Equals this divided by. Oh, sorry. Yeah, this divided by the expected. And then this is equal to the sum of all those. Now that's not your p-value, that is the, that's the test statistic, that's chi-square. So chi-square, remember in the first one it was 34, in the rock, paper, scissors example. Now it's 0.47. That value is also not in the table. Okay, the lowest value in the table is 3.2. This is table F I'm talking about. But we know that it's greater than 0.2019. Actually, the number of degrees of freedom is now 3. So all we know is that it's greater than 0.2035. Okay. But that's enough information to know if we reject or accept. Here's the exact p-value. So do we reject or accept? Accept. So Gregor Mendel is stoked because he was like, yeah, it does match, and it could be that there's a very high probability that my distribution that I observed in real life matches my theoretical distribution. So my theory could be correct, unless there's some other way to explain that theory. Well, it's your alpha value. Yeah, so it's the probability of rejecting. It's a probability that you're going to reject the null hypothesis when it's in fact true. So, yeah, it's a probability that you get it wrong if you did reject it. So, yeah, it's really strong evidence in support of the null hypothesis being correct. So disapprove Mendel's theory of genetics? Yeah, I mean, well, it at least indicates that the theoretical proportions for P phenotypes were correct, or most likely correct. Right? So that's good. So I guess I already showed this slide, but this is just kind of a summary here. And this can be done with anything. We could do this with the binomial distribution or Poisson distribution. In fact, we're actually going to get a little bit more practice with that next week. The spatial. Remember when we did the spatial count the tornadoes in I forgot what it was, but it was some variable we counted up. We're going to do that a little bit next week when we talk about spatial inferential statistics. But we can do that for that. We find out if the expected counts for each cell match the observed counts. That's what this is testing. Because in real life, they rarely match them exactly. But we have the question, could this, if this was the theoretical distribution, could this distribution that we actually observed be from that theoretical distribution? It's always one-tailed. You compare it. It's always the degrees of freedom. It's always the categories minus 1. Here's one more example. So in British Columbia, Canada, evidently, kind of like in California when I was a kid, that's changed now, but when I was a kid, the cutoff for entering school was December 31st of that year. So you could enter school in January before you had turned, what was it? Was it 5 or 6? 5? 4? So basically, when I was a kid, you could enter when you're still 4, as long as you're going to turn 6 by December 31st. That's pretty young, right? So the cutoff here is older. It's like, I think it's like the first day of school, right? Something like that. I don't know.
I'm home in September.
In September. Yeah. All right. So this test was done. It was an actual test. This is an actual test. It was done to see if children born late in the year, so they're younger than their peers, are more likely to be diagnosed with ADHD, with ADHD. So the question is, are these kids, do they really have ADHD, or are they just younger kids that aren't ready for school yet? So almost 1 million school children aged 6 to 12 years old in British Columbia were studied. Okay? This is an actual study, not a made up, well, I guess Gregor Mendel wasn't made up, we were just testing his theory there. Okay, so the way that we would do this is that, first of all, are births uniformly distributed throughout the year? No, they aren't. So if you look at this, they're kind of close, but they're not exactly uniformly distributed. So we've got less in the winter. The most actually happen in April, May, and June, the spring. Okay, so that's kind of my birthday's in April. And then almost an equal amount in the summer, and then it goes way down in the fall. Not hardly anybody, but it goes back down. So we get this kind of cycle every year where there's more births in the spring and summer than there are in the fall and the winter. Okay, and that's important. It's important to have this because if we just assumed that it was equal, we would be asking a different question. So we're looking for the distribution of counts to be related like this. In other words, the ADHD counts should be relatively the same for each category. Okay? In other words, if you're born here, you should have relatively equal chance to be diagnosed with ADHD as you are born here. Well, look at this. So going into a particular year, these people are actually the older people, these two, and these people are the younger people. These are the very youngest. These are the second in July through September. Okay? So basically the question is, what if we move the cutoff up to here? But it's actually kind of interesting that we get a higher number here. Okay? But we're just looking at the ADHD diagnoses. We've also got this to come into play. Is this really that much bigger than that based on these proportions? That's the questions that we're trying to answer. So what we say is, okay, these are the real proportions of births. So if we wanted to redistribute these and get an expected count, then we can compare ADHD diagnosis to expected counts to get to a chi-square value. All right? So we could again copy this. Whoop, that didn't work. Copy this into Excel. Just create a new sheet. I like to just do the paste special. All right, so to get the expected, we have to sum up everybody again. Get a total. And now I'm going to do that thing where I renamed it N. Oops. I guess since it's in the same sheet, I can't rename it N. I'll just call it N2, I guess. And then I can calculate the expected counts always as the total times the proportion, the expected proportion. But I have to change this to N2 if I don't want it to fill down right. Whoops. Did I call it N2? Oh, I can't call it N2 because N2 already exists. Okay, I'm going to call it total. There we go. And so I'll call this total times B2. And fill down. So it's interesting that we would actually expect there to be more ADHD diagnosis in this month. I mean, this for these 3 months than for these 3 months. Almost 5,000 more. I mean, sorry, 500 more. Just because there are more people born in those months. So the difference here is actually smaller than that. That's kind of interesting. So now we're going to be able to see if ADHD diagnoses match the proportion of people, or if, in fact, they don't, and we probably need to readjust when the kids go into school. So what we could do here is say equals chi-square. Let's just do the chi-square test this time. The ADH diagnosis and the expected counts, and press enter, and that is the value. Is that really, really big or really, really small? That's really, really, really small. So what does that say? Is this, do these match, do these expected counts match the ADH diagnosis counts? No, they don't. We reject that they match the distribution. And this is very, 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 very small. And so we say that the expected counts do not match this proportion, and therefore we conclude that the age grouping does have something to do with ADHD diagnosis. In other words, where you're more likely to get not misdiagnosed, but diagnosed with ADHD, probably misdiagnosed with ADHD if you're younger, right? I guess it would be interesting to look and see in an area like here if it makes any difference. If it's always that the younger kids are going to be the ones that are, so like even what I'm saying is even if you move this up, what would happen, right? So the July through September might always be the younger kids. I mean, might be the younger kids, and they might get overdiagnosed as well. But so it doesn't necessarily prove that we need to move the date up. It's just an argument for it that the younger kids are more likely to be tested. Now, here's just a second example with boys instead of girls. So we could, messed up, do the same thing. And these are the proportion of girls born each of those months. So the expected, we would sum those up. And then call this G tot for girl total equals this times that. Fill down and say equal to chi squared test actual in expected, and there is the chi squared. Now it's still it's still very, very small, so it's significant. Still significant. Yes, it's not quite as small, but it's still really, really, really small. In either case. All right, so that's chi-square with basically just one set of categories. So what I mean by one set of categories? Well, everybody that's sampled, or everything that's sampled, falls into a single category. So you could use this, like, let's do more of a nature example. So if you sampled a number of land cover types, okay, and you decided that a certain region was characterized by having this proportion of agriculture and this proportion of forest and this proportion of urban. And so you sampled it, and you could test whether or not your region met those criteria, had those same proportions of forested, urban, and regional. Like if you were studying and trying to decide if region A was similar to region B in terms of the way that they had developed. Okay? Anything you can divide up into categories. You could use it to to look at how accurate a map. I mean, there is just plain old map accuracy, but you could see if different categories were mapped with similar amounts of accuracy. So if you could say, I theorize that my map is just as accurate in forested areas as it is in urban areas, and so you could find a statistic. It's accurate or not accurate, and then forested or not forested, and come up with an expected value for that. So, those are just a few I could think of off the top of my head, but anything that is that's categories that you can compare to an expected distribution, you can use this for. Okay. You can also use the chi-square. Just a second.